Okay, students, this is section 5.4, exponential functions integration. So you've learned in the past that the derivative of e to the x equals e to the x, and so therefore you can assume that the integral of e to the x is also going to be e to the x. Now you will have your chain rule involved, so looking at the integral of e to the u would be e to the u du. So we will have to look at that. Let's just recall a few things about E. The definition of E is, well, one definition. If you compose the natural log with E, you just get back 1. All right, so looking at right here, ln of E is equal to the integral from 1 to E of 1 over t dt. And that's because the integral, remember, of 1 over t is the natural log. And so that would be, like using the fundamental theorem of calculus, where you integrate from 1 to a number, and so that changes it to that variable. I don't know if y'all can see that e or not, but the upper integral, upper integrand is an e. Let me try and darken it a little bit. All right. And so that equals 1 because if you integrate 1 over t, you get the natural log of x, but with you could just look at it as basically looking at the natural log of e. You're filling in that x with an e minus the natural log of 1, and that's 0. So natural log of e just equals 1. Okay? All right, so this is the little proof at the bottom. To prove property 1, use the fact that natural log of e to the x is equal to x and differentiate each side of the equation. So this is showing you that the derivative of e to the x is equal to e to the x. If you take the derivative of natural log of e to the x, since they compose, then you take the derivative of the right side, which is just your x. So this is where I'm at. All right. The derivative of natural log of x is 1 over e to the x times the derivative of e to the x. And since we know that the derivative of, I think I confused myself. The derivative of x is 1, so we're right here, okay? And then they just isolate the derivative of e to the x by multiplying both sides of this equation by e to the x. So I'm going to erase my arrow. All right, and so that shows you that the derivative of e to the x is just e to the x itself. Okay. All right, so that was really something we should have gone over back in the derivative of e to the x, but I decided to add it here. It's just a little proof. So since our derivative of e to the x is e to the x, then the integral of e to the u du is e to the u plus c. All right, so in this problem, our u would be 3x plus 1. Okay, so we're needing to, look at the fact that what e is raised to has a derivative itself. So to get it in the e to the u form, du would be 3 dx. So I can divide both sides by that number. So dx is 1/3 du. So we need a 1/3 in the front of our integral symbol, and then we're just integrating e to the u du. So that's kind of your objective. You're trying to get something into the form of the integral of e to the u. So 1/3 e to the 3x plus 1. This is just going back and subbing in what our u was. Don't forget the plus c. All right, so the next one we have the integral of 5x e to the negative x squared dx. So looking at your exponent being a negative x squared, and we know that has a derivative, so let's let u equal that. the derivative would be negative 2x dx. So we want to divide by that negative 2 coefficient. Remember, you can only divide by a coefficient on both sides. So that becomes a negative 1/2 in front of our integral symbol. Okay, we also have that 5, which can be moved to the front. So I'm going to put a 5 out to the front. Okay. So the x and the dx, that's actually your du now. So replace everything with u's. So this becomes integral e to the u du. So that's negative 5/2 e to the u plus c, or negative 5/2 e to the negative x squared plus c. Okay, and remember, we can always check these by taking the derivative. All right, so this example, we have an a and a b. So let's try letting our u equal the 1 over x, which I'm going to rewrite that as x to the negative 1. Okay, so the derivative of that is negative x to the negative 2 dx, which we know we could rewrite negative 1 over x squared if we flip it and make it a positive exponent. So we see we have that x squared in the bottom. All we're missing is the negative 1. So we can put a negative in the front of our integral symbol, and then this just becomes simply e to the u du. Okay, so it's negative e to the u plus c. And of course, we go back and substitute what our u was. You can leave it x to the negative 1, or if you want to go ahead and rewrite it as 1 over x, you can. Okay. Part B looks like our exponent is cosine x, so let's let u equal cosine of x. The derivative of that is negative sine x dx. Okay, so we're just missing a negative. We have our sine x dx, so we need a negative in front of our integral symbol. So our problem becomes negative e to the u du. So negative e to the u plus c, and our u was cosine x. Okay, so these have been pretty straightforward so far with just using your u substitution. All right, example 10, we're finding areas. So remember, the area is just the integral, the definite integral, the area under the curve. So looking at the integral from 0 to 1 of e to the negative x dx. So just a quick little sketch. I'm not going to sketch all of these, but e to the negative x, that's just your decreasing exponential. All right, and so we're looking for the area between 0 and 1. So if we just let that be 1, we could just kind of block it off with like a vertical line, and then you're just looking for what I just highlighted, that area under the curve. So it's the integral 0 to 1, e to the negative x. All you really need is a negative in the front, so I'm not going to worry about writing out the actual u substitution. So it becomes negative e to the negative x, evaluated from 0 to 1. All right, so negative e to the negative 1. This is now using fundamental theorem of calculus, so capital F of B minus capital F of A, and then minus a negative e. Well, there's no such thing as negative 0, so I'm just going to put 0. So this becomes negative 1 over e, if you want to flip it, plus 1. E to the 0 is 1. Or you can say 1 minus 1 over e. If you plug that in a calculator, you're going to get some kind of decimal. Okay. B, the integral from 0 to 1 of e to the x over 1 plus e to the x dx. All right, so this one, You can't split it up because you have a binomial in the denominator. So let's let u equal the denominator, because I do know that the derivative of e to the x is e to the x, which I see we have in the numerator, right? So that looks like it'll work out perfectly. We can put our du over, and then our whole denominator is just u. So we're really just integrating du over u, which you learned previously was the natural log of the absolute value of u. So we don't have a plus c here because this is a definite integral. All right, so let's put our u back in, 1 plus e to the x, and we're going to evaluate from 0 to 1. Okay, so it's natural log, absolute value, 1 plus e to the 1 minus natural log, absolute value, 1 plus e to the 0. Well, this is just natural log, absolute value of 1 plus e. And then e to the 0 is 1, so it's minus natural log, absolute value of 2. All right, now you could leave it like this, or you could use your properties of the logs and write it natural log of, and since 1 plus e is positive and 2 is positive, you could actually drop your absolute value bars. So natural log of 1 plus e all over 2. You could put it in a calculator and it should come out to be about 0.62. Okay, just depends on, what the question asks, how they want the answer written. All right. C, we have integral -1 to 0, e to the x, cosine of e to the x, dx. Okay, so let's try just letting our u equal e to the x. That's your angle. So the du is e to the x dx. And we see that's exactly what we have outside. Okay, so we're integrating -1 to 0, the cosine of u du. All right, so integral of cosine is sine, but remember we're plugging back our u. So sine of e to the x evaluated from -1 to 0. All right, so plug it in. So sine of e to the 0 minus sine of e to the -1. Well, anything to the 0 equals 1, so this is really sine of 1. I'm going to use a parentheses around that. Minus the sine of 1 over e. And that's the exact value if you had to leave it exact. If you needed a decimal, plug it in your calculator. That's radians, 1 radian and then 1 over e in radian mode. So about 0.48. Okay. All right, so this is another area problem. Find the area of the region bounded by the graphs of the equations. Use a graphing utility to verify your result. So you obviously don't have to do that because we don't allow the graphing utilities, but you could just, draw a graph out of e to the x. So we know it looks like this. Okay, so you're looking at from 0 to 6, x equals 0 to x equals 6. So we can just approximate our 6 right there. So we're looking at finding this area. All right, so 0 to 6, e to the x dx. So e to the x, evaluated 0 to 6, just equals e to the 6 minus e to the 0. So e to the 0 is 1. So this is our exact area. If you want a decimal approximation, it's about 402.4. So it's a pretty big area. All right. Sorry, I think it skipped a page. Okay, so just some more practice. Let's let u equal 1 over x squared. 1 over x squared can be rewritten x to the negative 2. So du is negative 2 x to the negative 3 dx. That can be rewritten negative 2 over x cubed dx. All right, so we have that negative 2 coefficient. It could be divided on both sides, and so we could actually put, I'm going to use a different color to show that. If I divide both sides by my negative 2, okay, that leaves you with 1 over x cubed dx, which we have. So we need a negative 1/2 in the front of our integral. And then our problem just becomes e to the u du. All right, so that stays negative 1/2 e to the u plus c. And then don't forget to plug in what your u was. So e to the 1 over x squared plus c. Okay. All right, so look at our next one. So typically what happens on these, your bottom, if your denominator is not a monomial, it's more than one term, that's usually what you're going to try first. Let your u equal that. We had one similar to this, if you remember just a minute ago. Okay, but the derivative of 1 is 0, but the derivative of e to the 2x is actually 2e to the 2x. So don't forget chain rule is involved here. The derivative of your exponent needs to be multiplied. So 2e to the 2x. All right, so let's get rid of our 2, dividing it. So we need a 1/2. All right, so this e to the x dx, I forgot you put a du there by accident. Let me switch that around. That should have been dx. All right, our e to the 2x dx, all of that is our du, and then our bottom is u. Well, what's the integral of du over u? Natural log, absolute value of u. Let's see. All right, so it's 1/2 ln absolute value of 1 plus e to the 2x plus c. Okay. Sorry about that, y'all. The pen sometimes, like when I press the page to go forward, it skips a page. All right, so let's try letting u equal the bottom again. That's the only thing that really makes sense. So the derivative of that is e to the x, and then it's minus e to the negative x dx. So I'm going to put parentheses around it since it's a binomial. All right, that is the numerator. So we have du in the numerator over u in the denominator. Okay, so straightforward, du over u, natural log absolute value of u plus c, and then of course put your u back in. So natural log absolute value e to the x plus e to the negative x plus c. Okay. And then the last one, so since this is being divided by a monomial, you can actually split it up into separate, basically separate problems. What I mean by that is you're dividing everything by e to the x. Okay, so everything in your numerator gets divided by your denominator. And you can see once you do that, it's going to be pretty easy. All right, subtract your exponent, so that's e to the x. And then here it's just 2 because your e to the x's cancel. And then you can bring that e to the x up and call it e to the negative x. All right, put your symbol. So integral of e to the x is e to the x. The integral of 2 with respect to x is just 2x. And then the integral of e to the negative x is negative e to the negative x. And then plus c. Okay. So hopefully that lesson was pretty easy. Shouldn't have been too difficult for y'all. If you have any questions, of course, let me know. Thanks.